Hello everyone and welcome to lecture. Today's lecture will be about optimization and specifically solving for the maximum and minimum value of a given function in an optimization problem. So specifically what we'll start with is talking about optimization in 1D for scalar valued functions. And what you'll hopefully recall is that the main theorem that we have for optimization in 1D is that the absolute max and min sometimes called the global max or min of a given function occurs at one of two locations. And this is specifically at either A, an interior critical point of the function, interior to the domain under consideration, or B, on the boundary. Of the domain. And a picture illustrating this is the following. Suppose we have a function of x. So we have some function of x, and we have an interval from a to b, and the function of x starts here at a, at this point right here, and then maybe looks like this, up until b, where it hits this value, and then it's right where we're considering maximizing and minimizing the function on this interval from a to b. You'll notice that the function that we've drawn has a number of different critical points. One here at x1, at x2, at x3, x4, and then lastly at x5. x3 is a critical point of type 2. Where the derivative does not exist. And the other critical points, x1, x2, x4, and x5, are all critical points of type 1. Where the derivative at the point is equal to 0. Where the instantaneous rate of change at the point is equal to 0. And you see very clearly from this example function that all of the critical points are local maxes and or mins of the function, but the global max and min only occur at two separate points. The global minimum of the function occurs here at this critical point at x3, so we say that x3 is an absolute max or absolute min of the function on the interval from a to b, and the absolute maximum of the function doesn't occur at any of the interior critical points, but it occurs on the boundary. So it occurs at the boundary point of a. So this is a nice example function showing exactly where the maximum and minimum, the absolute max or global max and min of a function can occur. So it illustrates this theorem for us. So it turns out that for multivariable functions, we have this exact same theorem, almost word for word. And we'll visualize that for functions of two variables, but this theorem actually applies for functions of any number of variables as well, which is why we can actually state and solve optimization problems in any number of dimensions for any number of functions. Definitely becomes more complicated for higher dimensions. But we'll look at what this says for 2D right now. And I guess we'll state the theorem in general. And the theorem says the following. The absolute maximum or minimum value of a function of n variables on a closed bounded region and we'll call this region omega in n-dimensional space occur at either one of two locations. The first possible location is at an interior critical point, inside the region omega. So remember, this is a point of two possible types. The first type is where the gradient of the function at a point is equal to the zero vector, or all of the partial derivatives are equal to 0. Or a point of type 2 where one of the partial derivatives at the point does not exist. You'll remember this is our second type of critical point. So the absolute max or min of a function occurs either at an interior critical point or at a point on the boundary of this region. So a boundary point of the region omega. So this is our main theorem for optimizing functions of more than one variable. In 2D, we know we have multiple different ways of visualizing this this statement. I think a nice way of visualizing it in 2D is to look at the level curves of a function, and specifically, if you have some domain that you're interested in optimizing over, it could be very complicated. Maybe it looks like this, and then this is the region D that we're optimizing over. And then maybe the level curves of the function look like this. So the function shown here, you have a possible min or max right here, a possible max right here, possible max or min other points on the boundary, but all within the set D. You have multiple different points on the boundary, which could be max or mins, and you also have that there are a number of different interior points, which could be maximums or minimums of your function. So a lot of times, just looking at the level curve plot or a density plot in 2D of the function will give you a good idea of where the max or min is. But you see that this is consistent with that theorem. It's saying that at the interior critical points of this function, of which there are, for the drawn example, there are 2 interior critical points. The global max or min of the function could be either at these interior critical points or on the boundary, as the only 2 possibilities for maximizing the function. Another nice graphical interpretation of this, as we've seen, is for a function of 2 variables, we can plot the graph of the function, so the surface plot of the function. If we make a third axis and we visualize this third axis, then what this looks like is you'll have an x-axis, a y-axis, and a z-axis, and some domain down here in the xy plane that you're optimizing over. And then the function itself, if you plot the surface plot, z equals the function of x and y, you could have, say, a global maximum right here, maybe the minimum of the function occurs at an interior critical point right here, where the function kind of goes down and then it dips down maybe to this minimum. And the global maximum maybe occurs here on the boundary. And then for all other points, maybe the surface looks kind of like this. So for example, this could be a surface plot of a given function of multiple variables, but you see that you have maybe the global minimum of the function occurs at an interior critical point where this is the lowest possible value of the function, and then the function just sort of, the surface of the function maybe hits a maximum right here at this point right here, where this is a boundary point on the domain that you're considering. The idea and the hopeful generalization that you can see is that this applies in general, right, for any number of variables. So even in 3D, say, if you're considering, say, like the level surfaces of a function, where you have a function of 3 variables, say, so in both these examples, we have some domain D that we're optimizing over, and very often in 2D, we'll use the notation D for a domain. But this also applies in 3D as well. So say, for instance, you have some region, some 3-dimensional region, omega. This is a 3-dimensional surface. And you have possibly a temperature function or some other function of 3 variables that's defined on this surface omega. This theorem still holds, and it still says that you can find the absolute max and mins of your given function on this 3-dimensional region at either an interior critical point of omega, to the domain omega, or lying on the boundary of omega, which is going to be, in general, some type of surface. So this is our main theorem that we can use. We're going to see that there are two main problems that we have to consider in any number of dimensions when optimizing a multivariable function. And the big issue here is that the maximum and minimum values of a function severely depend on the domain on which we're optimizing over, which are typically problem dependent. And this is the same problem that you face in 1D as well. The global or absolute max and mins that you solve for in 1D are heavily dependent on the domain at which you're optimizing over. So let's say we have some function of 2 variables with 4 critical points. If you were to say pose an optimization problem on this domain, call it D1 here, in general the solution on this domain D1 is going to be distinctly different than the solution to an optimization problem on this domain D2. You can label the critical points, say like P1, P2, P3, and P4, and you can see clearly why. For both of the functions, or for both of the domains, you're dealing with the same function of 2 variables, but the optimization problem on D1 gives us that the 2 interior critical points to the region D1 are P1 and P2, and you potentially have a whole bunch of other spots on the boundary where there are maximums and minimums on the domain D1. For the domain D2, D2 definitely shares the critical point P2 with the domain D1, but it also, inside this domain D2, you have a new critical point, which is this P4 right here, and you also have a different boundary. So you have a whole bunch of other potential locations for a max and min of the function on the boundary. For both domains, P3 is outside of the interior of both of the domains. So this is not, P3 is not a possible max or min for either of these 2 domains, D1 or D2, because P3 is a critical point that's outside of both of the domains. But you have this exact same issue in 3D as well. If you were to say draw out a function of 3 variables and look at the potential max and min locations for 2 separate domains in 3D, you'll see that this exact same problem or potential problem pops up. Let's say again you have a function with four separate critical points, all located at different locations in 3 dimensions. And then you pose an optimization problem over some 3-dimensional domain. We'll call it omega 1. Where these critical points all lie inside of this region, omega 1. And then let's say you have a similar scenario where you have some other domain, omega 2, that only contains 2 of these critical points of our function of 3 variables. And you can also label these critical points very similar to the previous problem for a function of 3 variables. You still have the same issue where if you're doing an optimization problem on omega 1, the solution in general to that optimization problem will be either at those 3 interior critical points that are inside omega 1 or on the boundary. And same thing for omega 2. But for omega 2, you only have 2 interior critical points, P2 and P4, or on the boundary of that new domain omega 2. So this is definitely one potential issue that is very important. You always have to consider whether or not your critical points lie inside the valid domain that you're looking for to solve the optimization problem. The second issue, and an issue that is also very important to talk about, is specifically, you can see this in domain 1 here in this first example, is that you could have a piecewise defined domain. So here D1 is what's called a piecewise smooth domain, or a domain that can only be described with piecewise functions. So by breaking it into separate parts and dealing with each piece individually. In which case, this theorem still holds and it's perfectly fine, but you have to be careful to analyze every separate piece of the domain when you're looking for a potential max or min on the boundary. And this also holds in 3D as well. Most domains that are describable, in order to describe them nicely, you have to break them up into multiple different pieces. So a perfect example of that is a rectangular domain in which you have multiple different pieces that describe a rectangle. So if in 3D, say, you're trying to optimize a function over a rectangle, well, you're going to have to break that rectangle up into the 6 faces of the rectangle, all the multiple different faces, and consider separate optimization problems on each individual face. That's for a 3D optimization problem. Similarly, in 2D, if you're trying to find the maximum of a function over a rectangular domain in 2D, you're going to have to break that up into the rectangle, each one of the separate lines, the boundary lines or boundary curves of the rectangle. So in order to check the boundary for this example, specifically if we have this shaped domain, we'd have to break the boundary up and consider separately each one of these separate pieces to this domain right here. But what's nice is that this theorem still holds. So you'll see that the easiest optimization problems to solve on the boundary are problems with a nice smooth boundary that can be parameterized. And typically what we do for the first approach towards optimizing on a boundary is find the parametric curve representation for that boundary. So we use parameterization and parameterization of curves from a previous calculus course. Now, by the end of this section, we'll also talk about a separate method to deal with constraints like this, which is called Lagrange multipliers. But this will be for the topic of the next lecture. So let's visualize this and try to take a look at this with a specific example. And we'll keep it relatively simple. We'll try and find the absolute max and min of the function x times y on an ellipse. And just for argument's purposes, we'll deal with a very specific ellipse. We'll take the ellipse with a distance of 3 in the x direction and a distance of 2 in the y direction. So that's described by this algebraic equation right here. So what's nice is that we can typically, if we can draw the level curves of the function in a relatively straightforward manner, we can get a nice picture of where exactly we expect the max and min to occur of the function. And this is without even using that previous theorem, but that previous theorem holds in general regardless, which is really, really nice. So what I'll do is I'll draw the domain here that we're optimizing over in black, and this ellipse is the ellipse that stretches 3 in the x direction and 2 in the y direction. So it looks like this. Sometimes we call this a curve C, just for short, to describe this curve. And then this function, the function f of xy equals x times y, I'll draw the level curves of that in red. But to get the level curves, we fix the output of the function to be equal to some fixed c value, which gives us curves of the form x times y is equal to c. And we've seen that for various values of c, this gives us different curves. So, for instance, when c is equal to 1, you get the curve y is equal to 1 over x. When c is equal to 0, you get the curve x times y is equal to 0, or x is equal to 0, or y is equal to 0. When c is equal to -1, you get the curve y is equal to -1 over x. So the curve y is equal to 1 over x looks, when x is 1, that means that y is 1. When x is 2, that means that y is 1/2. When x is 1/2, that means that y is equal to 2, right here. This is enough to give us a very preliminary plot of this level curve. It looks like this. This curve corresponds to c being equal to 1. And you have the exact same picture down here in the negative direction as well. because this is the curve, y is equal to 1 over x. When c is equal to 0, you get the straight line going down at x equals 0. And you also get the straight line going across corresponding to y equals 0. So the function value on the axis is 0. And then lastly, when c is equal to -1, we use a dotted line to show the curve corresponding to the curve -1 over x. This dotted line corresponds to c equals -1. It's a dotted curve, not a dotted line. Same thing right here. And so just looking at this function, you'll see, well, we expect there to be a saddle point. So at least a saddle point at the origin right here. And we actually expect the global minimum of the function to arise at these 2 points, because the function is decreasing as you move in those 2 directions. And we also expect the global maximum to arise right here and right here, because the function is increasing as we move in that direction. This is a great example, without even going through and doing the computations, of why the theorem we showed before really makes a lot of sense. Specifically that we expect there to be one interior critical point of this function, but we expect that point to be a saddle point, and we expect the global max and min, or the absolute max and mins of this function, to not be inside the domain, but on the boundary. And when we go through and do the computations, this is exactly what we find. So the first step for this function is to find all interior critical points. And this is done by searching for points of both type 1 and type 2. We don't expect there to be any critical points of type 2. Because the function f of x, y equals x times y is a quadratic polynomial. So there are no bad points. It's a nice function of x and y, and there are no points where the function itself is a bad function, or the derivatives of the function do not exist. There's no points like that. So if there are any critical points, the only critical points that we expect are critical points of type 1. Or where the gradient of the function at that critical point is equal to the 0 vector. So for this function, this means that if we solve for these points, the x partial derivative of the function is going to be equal to 0, and the x partial derivative of our function is the x partial derivative of x times y, which is y, and the y partial derivative of our function is equal to x. So the only solution to these two equations, the system of equations, is the solution x equals 0, y equals 0. Now if you go through and do the second derivative test on this point, 0, 0, you'll definitively show that it's a saddle point, because fxx is equal to 0, fyy is equal to 0, and fxy is equal to 1, So the discriminant, which is fxx times xyy minus fxy squared, is equal to -1 or less than 0. So this is a saddle point, which is exactly what we predicted from the level curves of the function. So what that means is that because it's a saddle point, it's not going to be the global max or min of the function, because there are regions around that point where the function's higher than that point and also lower than the value at that point. And you can even check that the function at that critical point at 0, 0 is equal to 0 times 0 or 0. So the function value at that point is 0. And what that means from our theorem is that we're kind of forced now to look on the boundary. And what's nice about this example is that the ellipse is a smooth boundary and can be entirely parameterized by a nice, very, very nice relation. Now, you always want to remember that the more complicated the boundary, the more difficult part B is going to be, because you're going to have to break it up into multiple different parts and possibly parameterize multiple different parts of the boundary. But we can parameterize the ellipse as follows. So the main idea with part B is break the boundary up into as many pieces as you need to parameterize it correctly and solve optimization problems for each individual piece. In this case, with the ellipse can be parameterized very similar to the circle. We talked about this a little bit before, that we can say that x is going to be 3 times cosine theta, and y is going to be 2 times sine of theta. This is for all theta between 0 and 2 pi. And what this does is it gives us the x coordinate and the y coordinate in terms of that one theta, that angle theta, for every single point on the ellipse. So for instance, right, this point right here is given by the angle, well, this angle is 90 degrees, or pi over 2, and this looks like it's about 1/3 pi over 2, so pi over 2 over 3, which is pi over 6. And the correct x coordinate and y coordinate of that point can be found by directly plugging into this parameterization. So if you plug in theta equals pi over 6 into these two equations, you get the x coordinate and the y coordinate of that point on the ellipse. So this is the correct way that we've talked about of parameterizing the ellipse curve. But in general, if your domain has multiple different pieces, maybe there are lines or different pieces, you're going to have to do this process for each individual piece. Luckily for us, the ellipse has a very nice parameterization, so we can just focus on the single parameterization. But it's important to realize that for more complicated domains, you can still do this process. You just have to consider each individual piece of the domain individually. So the first step in this process is parameterizing the domain. into the multiple different pieces that describe it. And the second step is considering the composition. Specifically, the composition of the function. In our case, it's the function that we're optimizing, so f, and how it depends only on the domain, so for points on the domain. So we have our parameterization, and we're going to take this parameterization, which kind of picks out points on the domain as a function of theta. So one parameter for a function of two variables, so for a 2D domain, and we're going to plug these 2 points always into the function itself. Now this, through composition, creates a single variable function, which you can call anything you want, but typically I'll call it h of theta or g of theta. So h here, remember, depends on x and y through the function f, and both of these things depend on the parameterizations. They both depend on theta. And what that means is that we can actually go through and use our multivariable chain rule to figure out the derivative of h of theta. Because this is a single variable function, all of the rules from single variable optimization hold. If I want to solve for a maximum or min of theta for theta in this interval, so for theta from 0 to 2 pi, right, what we needed to do is we need to look for interior critical points of h of theta inside this interval, which is points where either the derivative of h of theta does not exist, or points where the derivative is equal to 0. So there are no points for h of theta, because h of theta, if we directly plug in, you can for this example, it's not always straightforward to plug in, because sometimes it's a little bit function can get more complicated. But for this, it's just going to be x of theta, which is 3 cosine of theta, times y of theta, which is 2 sine of theta. And you see the h of theta here, the function on the boundary is just 6 times cosine of theta times sine of theta. So for this example, it's relatively simple to figure out what this function is on the boundary. So what's nice is that you can use the multivariable chain rule, that h prime of theta is going to be equal to the f, or the x partial derivative of f times x prime of theta, and then that's going to be plus the f partial derivative with respect to y times y prime of theta. You can always use the multivariable chain rule if you want to go through and do this. But you can also say, if you have a simple enough function like this, you can go through and take the normal single variable derivative. So you have a lot of freedom in here when calculating this h prime of theta. But the main idea is that for the interior critical points on this interval, for this function h, right, there's no interior critical points of type 2. And using either the multivariable chain rule here for h, or the normal single variable derivative of this function, right, you can go through and figure out how many there are of type 1. And we'll just do the normal derivative of the function, 6 times cosine theta sine theta, which in order to evaluate is going to require the product rule here. So it'll be 6 times negative sine theta, which is the derivative of cosine, times sine of theta, plus cosine of theta times the derivative of sine of theta, which is going to be cosine of theta. This is the product rule applied to this function right here. So h prime of theta is going to be equal to 6 times cosine squared of theta minus sine squared of theta. And this is a critical point of type 1 that we're solving for, so this is going to set this equal to 0. And when you look at this equation reduces to saying that cosine squared of theta is equal to sine squared of theta, or taking the square root of both sides, we get that the absolute value, it says, of cosine of theta has to be equal to the absolute value of sine of theta. And any point theta that satisfies this condition gives us an interior critical point, interior to the interval for theta from 0 to 2 pi of this function h itself, because it means the function h prime is equal to 0. And the solutions to this this equation right here are exactly the following 4 solutions. Right? It's whenever the angle theta gives us a value of 1 over the square root of 2 or negative 1 over the square root of 2 for either of these two values. So you have 4 possible values of theta where this happens. One is at pi over 4. One is at 3 pi over 4. Remember, pi over 4 actually corresponds to 45 degrees. And so on and so forth. All of these directly give us a value for either cosine or sine equal to plus or minus the square root of 1/2, or 1 over the square root of 2. So pi over 4 is one value, 3 pi over 4 is another value, 5 pi over 4 is another value, and 7 pi over 4 is the last possible value. And if we want, we can even list out the x values at each one of these and the y values at each one of these to figure out exactly what x values and y values these correspond to. Right? For pi over 4, you have that x is equal to 3 cosine of pi over 4. So x is going to be equal to 3 times 1 over the square root of 2, or 3 over the square root of 2. For 3 pi over 4, when you have, right, that corresponds to the angle of this angle right here, you have exactly that x is going to be negative 3 times 1 over the square root of 2 when you directly plug into our parameterization. Same thing for 5 pi over 4, and then for 7 pi over 4, you'll have that x is 3 over the square root of 2 again. For the corresponding y values on this ellipse, you'll have that y is going to be at pi over 4 is going to be 2 over the square root of 2. For 3 pi over 4, it's also going to be 2 over the square root of 2. For 5 pi over 4, you'll have that it's negative 2 over the square root of 2. And for 7 pi over 4, you'll have that it is also negative 2 over the square root of 2. So these are potential max and mins on the boundary. And lastly, we'll write it down the function values at each one of these points. The function value at this first point at pi over 4 is going to be, the function, remember, is f of xy is equal to x times y. So it'll be 6 over the square root of 2 times the square root of 2, or 2. So that's just going to be equal to 3. It'll be negative 3. Similarly, at 3 pi over 4, it'll be positive 3 at 5 pi over 4. And it'll be negative 3 at 7 pi over 4. So these are all potential max and mins of the function. And the last thing we need to do is, again, look at the two boundary points of that region from 0 to pi, 2 pi. So at theta equals 0 and theta equals 2 pi. But at theta equals 0 and theta equals 2 pi, in both cases, either x or y is 0. So the function values at these 2 points are going to correspondingly be 0 as well, 0 and 0 for both of these two angles. So it's important to check and compare now. We have to compare these two values with these 4 values, and then also compare to the point from A, which is this value right here. And it's clear that the maximum of all of these values and the minimum of all these values give us the global max and min of this function. And sure enough, the straightforward candidate is all of these values right here. And you can directly see this, that saying the global maximum of the function on the ellipse, on this domain, is 3. And this occurs at this point, so x and y, as well as at this point right here, x and y, which I'll color in pink here so you can kind of see this directly. So the global max occurs at this point right here, and at this point right here, and I'll color in light green the global min of the function. It occurs here and here, where the function hits a value of negative 3. The value of negative 3 occurs at this point right here. And this point right here. And there you have it. So this is a great example for showing in general how to go through and do this to solve an optimization problem. In general, the idea here is that we can go through and directly solve an optimization problem by comparing the interior critical points of a function to the boundary points of a function, to the possible max and mins on the boundary. And we'll see that with Lagrange multipliers, things become a little bit more easy to deal with. The specific problem of solving for max and mins of a function on the boundary become a little bit easier to deal with. So for our last example, I'll go over an example of a piecewise domain in 2D, which is it'll be a good example problem to show how to deal with a domain that's a piecewise domain for optimization of a function of 2 variables. Specifically, we'll talk about optimizing the function (2x squared minus 4x plus y squared minus 4y plus 1. And we'll optimize this function, so search for the global max and min over the following domain. consider you want to optimize this function over the triangular domain bounded by the line y equals 2 and the line y equals 2x. So we'll say that y equals 2, this is y equals 1, say, y equals 2. So the line y equals 2 is this line right here. And the line given by y equals x, well, y equals 2x. X goes over by 1. It's exactly this line right here, the line going up through the origin and hitting that point right there. Just move it up a little bit to make it look a little bit more correct. It's going to hit this point right here. And this is the line y equals 2x. So the region bounded by the line y equals 2 and y equals 2x is exactly this domain right here. In which case this domain has a couple of different boundaries. It has the boundary corresponding to x equals 0. It has the boundary corresponding to y equals 2. And it has the boundary corresponding to this line y equals 2x. Our procedure is still directly the same as before. The first step is to identify all interior critical points. That's step A. And for this function, because it's a quadratic polynomial, there are no interior critical points of type 2, only critical points of type 1. So this is where fx is the partial derivative with respect to x. This is going to be 4x minus 4 is equal to 0. And simultaneously, the y partial derivative, which is 2y minus 4, is equal to 0. So the solution to this system of two equations corresponds to x is equal to 1 and y is equal to 2. And you'll notice that this actually corresponds to this point right here. This is the point x equals 1, y equals 2. So it's not actually interior to the domain, but it's still within the domain of consideration. So this is a potential max and min at the point 1, 2. And at this point, our function is going to be what you get when you plug this point in. So it's going to be 2 times 1 squared minus 4 times 1 plus 2 squared, which is 4, minus is 4 times 2, which is 8, plus 1. So our function value at this point is going to be negative 2 plus negative 4 plus 1, or negative 5. This is a potential max or min of our function. So this concludes our part A. And then for step B, we have to go through and investigate this at each different possible boundary or piece of the boundary. So for piece 1 of the boundary, we'll take this as x equals 0 and y between 0 and 2. For this piece of the boundary, our function is just a function of y, and it's the composition of x equals 0 and y, for y from 0 to 2. When we plug this into our function, we end up getting the function y squared minus 4y plus 1 which doesn't have any critical points of type 2, only a potential critical point of type 1 when h prime of y, or 2y minus 4, is equal to 0. And this happens when y is equal to 2. So according to our optimization theorem, we now have, for this boundary piece, 3 potential max and mins. A potential max and min at 0, 0. A potential max or min at 0, 2. And a potential max or min at this interior critical point, which is 0, 0, 2 as well. It's the boundary point of our domain. So really we only have 2 potential absolute max and mins. The function value at each one of these points is at 0, 0, the function is 1 when you plug in, and at 0, 2, the function when you plug in is equal to negative 3. So this is the first piece of our boundary. The second piece of our boundary consists of, we'll call it the top piece. So we just did the first piece, which is this left piece. The second piece of the boundary is when y equals 2. And x is between 0 and 1. For this piece, our function, our single variable function that we have to consider, is a function of x. Specifically, it's the function when you plug in x and y is equal to 2. Which is the function 2x squared minus 4x Then when you plug in y is equal to 2, you get 2 squared, which is 4, minus 4 times 2, which is 8, plus 1. So h of x is the function 2x squared minus 4x plus minus 3. So again, this is a polynomial function, so there are no critical points of type 2. The only critical point inside the domain from 0 to 1 is when the derivative of the function h is equal to 0, which corresponds to the equation 4x minus 4 is equal to 0, which gives us an interior critical point of x is equal to 1 for this function h. So from our optimization theorem in 1D calculus, this means that we have a couple different possible absolute max or min locations. Specifically, the potential absolute max and min locations are the boundaries of this line, this point and this point, and then also the point x equals 1, y equals 2, which actually corresponds to one of these boundary points. So the first potential boundary max and min for this function h of x is at the point x equals 0, y equals 2, then we solve for the other potential max and min point, which is x equals 1, y equals 2. So at 0, 2, we actually already solved for this. The function is equal to negative 3 when you plug in the point 0, 2, and at the point 1, 2, it's equal to negative 5. It turns out we already kind of solved for that point when it's also one of our interior critical points that we ended up solving for. And the last piece of this domain corresponds to the piece of the domain that is the bottom of the domain, or the line y equals 2x. And this is, again, for x between 0 and 1. When y equals 2x, this composition function, the function h of x, is going to be f at x, and then y equals 2x, which when we plug into the function f, ultimately will give us 6x squared minus 12x plus 1. Because this is a polynomial in x, there are no critical points of type 2, only critical points of type 1, and taking the derivative of this function gives us 12x minus 12 equals 0, or x is equal to 1 again. So the potential max and min for on this boundary right here corresponds to, again, it's x equals 0, 0, and then x equals 1, 2. Because this is our interior critical point for this function, on the domain for x from 0 to 1. You always have to compare the boundary to the interior critical point, but for this example, it's a nice example because it's giving us the same result. It's giving us a boundary point as well as this interior critical point, but you always have to compare these two values. So at 0, 0, the function we've already seen, we've evaluated it, it's 1. And then at the point x equals 1, y equals 2, the function is negative 5. So the final step of this procedure is to compare the results from A to B. And you see that the lowest value out of all of the values we've calculated is the value of the function at the point 1, 2. The function is negative 5 at 1, 2. And the largest value of the function is the value of the function at 0, 0. I'll circle that in red. So because of this, we conclude that the absolute maximum value of the function occurs here at the origin, and the absolute minimum value of this function occurs at the point 1, 2, where the function at the minimum value is negative 5, and the value of the function at the absolute maximum is 1. So this is a nice summary of how to do this even if you have a piecewise domain. It shows you that we can apply this procedure regardless of what the shape of the domain is, and even if you have a more complicated domain, it just requires your step B to have more cases. But this example will conclude today's lecture. Thank you very much for listening, and I hope you learned something and had a great day.